Hey everyone! If you've got a chemistry board exam creeping up and you're currently staring at a textbook full of organic reactions feeling completely, utterly overwhelmed, well, take a deep breath because you are in exactly the right place. Today's explainer is your ultimate crash course. We aren't just going to quickly review organic chemistry mechanisms, we're going to completely decode them. We are handing you the master key to predicting products quickly and accurately. The goal? For you to walk into that exam room with absolute, total confidence.
Let's just be completely honest for a second. Are you currently trying to blindly memorize hundreds of different reactions? Because if you are, you're basically playing organic chemistry on hard mode. The real truth is, organic chemistry isn't actually about rote memorization at all. No way. It's a highly logical puzzle. Every single reaction you see simply boils down to how electrons move and the stability of the molecules they create along the way. Once you understand the basic rules of that puzzle, you honestly don't need to memorize anymore. You can just predict what happens next.
So here's the exact roadmap for today's explainer. First, cracking the code. Second, critical stability trends. Third, substitution versus elimination. Fourth, mechanism shortcuts. And lastly, a rapid review. Let's get right to it.
All right, jumping right into Section 1, cracking the mechanism code. Okay, so let's set the foundation right away so that the absolute chaos of arrows and reagents on your exam paper actually starts making perfect sense. If you take literally nothing else away from today, please remember this formula. Mechanism equals electron movement plus stability. A mechanism is basically just the story of a chemical reaction, right? And those curved arrows, they're the words writing that story. An arrow always begins from an electron-rich area, like a lone pair, a bond, or a negative charge, and it ends up pointing toward an electron-deficient, positively charged target. If you know where the electrons are and where they naturally want to go, you can write the story yourself. Moving right along to Section 2, critical stability trends.
So when those electrons shift around, they often create these temporary, super unstable middlemen, and the stability of these intermediates dictates absolutely everything that happens next. The absolute most famous of these intermediates is the carbocation. By definition, a carbocation is just a positively charged carbon atom. It is highly reactive, sp2 hybridized, and sits in a perfectly flat, trigonal planar geometry. Just picture a flat triangle. Its intense instability and sheer desperation for electrons is the main driving force that pushes the whole reaction forward.
Now check out the stark contrast in stability orders here. For carbocations and free radicals, a tertiary carbon is the most stable, all the way down to methyl being the absolute least stable. Why? Well, because factors like hyperconjugation, inductive effects, and resonance all pitch in to stabilize that positive charge. But look at carbanions, the negatively charged carbons. The order completely flips. For carbanions, methyl is the most stable, and tertiary is the least. Knowing this flip is an absolute must for your board exam.
Seriously, grab a pen right now because these are guaranteed exam questions. I like to call these the exam power rankings. Look at the halogens. Iodide is the undisputed heavyweight champ here. It's the best leaving group and it's the strongest nucleophile. Similarly, when we look at acid strength, HI easily beats out HBr, HCl, and HF. Write these rankings down, visualize them, and just remember that iodine absolutely dominates these categories.
Let's tackle Section 3, substitution versus elimination.
This section tackles what is usually the biggest hurdle for most students. We are going to break down the big four, SN1, SN2, E1, and E2, so you can instantly categorize any reaction thrown your way. Okay, let's dive into this matrix. This is the ultimate showdown between SN1 and SN2 nucleophilic substitution. SN1 stands for substitution nucleophilic unimolecular. It's a clunky two-step process that forms our good friend the carbocation intermediate, and it strongly favors tertiary substrates in polar protic solvents, like water. Conversely, SN2 is bimolecular. It's a lightning-fast, single-step reaction with zero intermediates. It favors primary substrates because the nucleophile actually needs physical room to attack, and it works best in polar aprotic solvents, like acetone.
And this brilliantly illustrates how those different mechanisms actually mess with the final 3D shape of your product. Because SN2 is a quick, one-step process, the nucleophile is forced to attack from the backside, causing a total inversion of configuration. It's literally like an umbrella flipping completely inside out in the wind. But in SN1, remember that trigonal planar carbocation we talked about. It's completely flat, so the nucleophile can attack from the front or the back equally, giving you a 50-50 racemic mixture.
All right, shifting gears, let's contrast the elimination reactions. E1 is actually very similar to SN1. It's a two-step process involving a carbocation, and a weak base is totally fine. E2, however, is a single, dramatic step. It requires a really strong base to rip a proton away, and crucially, it needs a very specific anti-periplanar geometry to even happen. The hydrogen and the leaving group basically must be directly opposite each other for that double bond to form.
Now, when you finally form that double bond, you obviously need to know where it's going to go. The Zaitsev rule says the major product will naturally be the more substituted, most stable alkene. But, and this is a huge but for test day, if you see a bulky base on your exam, the whole game flips. Bulky bases are kind of like bouncers that are just too big to fit through the front door. They're way too big to reach the most substituted carbon, so they follow the Hoffman rule instead, giving you the less substituted alkene as your major product.
Next is Section 4, Exam-Winning Mechanism Shortcuts.
Consider this your tactical playbook. I'm going to give you the exact, rapid-fire shortcuts you need to confidently predict mechanisms on test day without any second guessing. On the exam, evaluate your nucleophile and your substrate first. If you see a strong nucleophile pairing with a primary, uncrowded substrate, boom, that is an SN2 backside attack. If you see a weak nucleophile and a bulky tertiary substrate, it's going to wait for the leaving group to leave, form a carbocation, and naturally go through the SN1 pathway.
Here is another massive clue examiners just love to drop. If you spot a strong, bulky base sitting over the reaction arrow, your brain should immediately flash a giant neon sign that says E2 elimination. A bulky base is just way too crowded to act as a normal nucleophile for a substitution. It has to act as a base, meaning an E2 elimination is for sure going to be your major product.
So, the crucial point is this regarding molecule rearrangements, things like hydride or methyl shifts. They are entirely dependent on having a carbocation. If you're dealing with SN1 or E1, a carbocation forms, which means it'll definitely try to rearrange itself to a more stable tertiary spot if it can. But if you're looking at an SN2 or E2 reaction, those happen in one quick step. No carbocation is ever formed, which means rearrangements are literally impossible. Do not ever fall for a rearrangement trick on an SN2 or E2 question.
Finally, always check the solvent sitting underneath the arrow. It's very often your ultimate tiebreaker. Polar protic solvents like water or alcohol stabilize ions, making them the perfect cozy environment for SN1 and E1 reactions to form those carbocations. On the flip side, polar aprotic solvents like DMSO or acetone don't cage the nucleophile at all. They leave it naked and highly reactive, perfectly setting up an SN2 attack. And finally, Section 5, the ultimate rapid review.
We are in the home stretch of this explainer now. Let's use this high momentum right now to lock these patterns permanently into your memory. Let's rapid-fire this summary chart. SN1, carbocation intermediate, resulting in racemization. SN2, no intermediate, resulting in a precise inversion of configuration. E1 is super similar to SN1. It has a carbocation, but it forms an alkene. And remember, electrophilic addition across double bonds? Yep, it also forms a carbocation and reliably follows Markovnikov's rule, meaning the hydrogen attaches to the carbon that already has more hydrogens.
Keep these golden exam points front of mind during your test. Resonance always equals greater stability for your intermediates. If you see an anti-Markovnikov addition happening, it's because of the peroxide effect, so look for peroxide written on the arrow. Remember that benzene's aromatic ring is so incredibly stable it vastly prefers electrophilic substitution over addition. And finally, strong nucleophiles drive substitution, while strong bases drive elimination.
I want to leave you with this exact quote from our source material. Instead of memorizing reactions blindly, understanding mechanisms develops logical thinking. Once the core concepts become clear, even complex reactions become simple and predictable. This absolutely validates all the hard work you're putting in right now. You aren't just some copy machine memorizing weird symbols. You now possess the logical framework to figure out literally any reaction they throw your way. You've got the rules, you've got the power rankings, and you've got the exact shortcuts. So, as you close this explainer and crack open those practice tests, I'll leave you with one final question to chew on. Are you ready to stop guessing, step into that exam room, and absolutely crush your test by using undeniable logic instead of fragile memorization? I really think you are. Good luck.